Okay, I want to give you just a brief introduction to one of the main reasons you're going to want to understand the material in this course, pre-calculus. Pre-calculus is a study of functions, and functions can model reality. What reality do you want to model? Do you want to model a business cycle? Do you want to model population dynamics in an ecosystem? Do you want to model something physical? Well, I won't say there's no end to the things that could be listed, but there are a great number of examples that I could give. But I'm going to start out with this example, which is fairly tangible. Here I've got a bucket. Bucket's got water in it, a couple of gallons. And if I fill the bucket or fill it partially, whatever, drill a hole in the side, water's going to come out. As the depth decreases, the pressure that pushes the water out is going to decrease. So the water's going to come out more and more slowly. So you have a stream, comes out fast, stream goes a long ways. Okay, comes out more slowly, stream doesn't go as far, and even less. That's something you can test. Take a softer, any kind of a plastic bottle, put a hole in the bottom, fill it with water, and watch what happens to the stream as the water comes out. If you're going to be an engineer, that's something you probably really want to understand. If in many other ways, you want to understand that, at least conceptually. Okay, so we could do a graph of the depth of the water versus time. And we can see intuitively from looking at this graph that the depth is changing more and more slowly with time. It takes more time to change the depth by a given amount as time goes on. Okay. Another model is going to be relevant to your financial future. If you invest money in let's say you put money into some kind of an account that yields constant interest. Well, that money is going to grow this way, according to an exponential curve. Okay, now I don't know if I made a good exponential curve. I don't know if this is a good curve for water depth. I don't know if this is a good curve for illumination, which I'll talk about in a minute. But there's a curve that tells you exactly, if you keep your money in the account, what that bank or what that entity owes you if you choose to withdraw it. And this has to be calculated exactly. Now, the depth of water in a container doesn't follow exactly the curve that I'm going to introduce later, but it's very close, and you would be hard pressed to, without sophisticated instruments, to measure any deviation from this model. Okay, now the same curve here for the money could model the population of, let's say, fish in a pond. Put a few fish in the pond, they reproduce, and those fish reproduce, and those fish reproduce. You have an exponential growth. Okay, now that's a little messier than the growth that you get from putting money into an account where somebody's responsible for giving you, for paying you interest, for compounding interest on your money. Now, because in a pond, there's little variations. The fish probably eat the small fish, and the more fish there are, the more small fish get eaten. Pretty soon, or at least eventually, the population is going to challenge the carrying capacity of that pond. There's only so much room in the pond. There's only so much food in the pond. So the exponential tendency is going to take, it is actually going to occur for a while, but then it's going to get fuzzy. It's actually going to kind of level off. And in any case, you're dealing with organisms with their individual behaviors and changes. So you don't expect the exponential model to be an exact model the way it would be with money. Okay. This example is an illumination curve. Now, if I want to measure how well, let's say I've got some writing inside of this little circle here. I want to measure how well the circle is lighted, just how intense is the light on that circle. So, okay, maybe how readable is the stuff in the circle. So I can use a light. You imagine this light bulb is lit, and I put the light here, and I've got a certain intensity of light. I could tell you how intensity of light is measured. I could tell you a lot about intensity of light, but I'm not going to do that. This isn't a physics class, okay? So here we have an intensity at this distance. So right now the thing's about this far away. Now I bring it back twice as far. Light's going to be less intense because the light from this bulb is spread out more by the time it gets here. And similarly, the further I move this away from here, the less intense the light is going to get. Now, if I do that in an otherwise dark cavern, let's say, the illumination is going to follow the curve that looks something like this. Illumination versus distance. The greater the distance, the less the illumination. I can quantify these things. Once I've got these graphs, I can say, well, I've got a scale on this graph. Here at time 80, what's the depth? Okay, well, I can figure that out. I can just say, okay, time 80, I'm at this point on the graph. I come over here, and what's this depth? Well, if this is 32, what's this? I can figure that out. I can do a pretty good job of finding the halfway point between here and here. It's going to be about here. That's going to be 16 because half of 32 is 16. And I hope you don't need to use a calculator to figure that out. A calculator gets in your way on simple calculations. Okay, you should be able to do simple calculations in your head and get away from the reflex of reaching for a calculator. And I really de-emphasize the use of calculators in this course. Okay, well, anyhow, then I can subdivide this. Halfway between here and here is about here. That would be 8. And then I subdivide that, divide that in half. And that's going to give me about 4 is right here. And this point, well, I could subdivide the 4. I could get 2 here. So that here I could say the depth looks like it's about 3. Okay. So at this point, time is 80. Depth is 3. Now, what's the depth at the first instant up here? Well, I'm not going to do a lot of subdivision, but I've got some idea of the scale. This distance here looks like it's probably about 3. So maybe here the depth is 33 more depth, 35. What's the time? Well, there it is. Let's see what it might be. Subdivide this interval. Subdivide this interval. So this would be 40. Actually, that's probably a little bit. Let's just say that this is pretty close to the middle of this interval. And let's just say that's 20. Okay, the time is 20. Now, if time is measured in seconds and depth is measured, let's say in centimeters, then I know that when the time is 20, we're 35 centimeters. When the time is 80, the depth is down to 3 centimeters. And there's a lot more that I could say about this, and we're going to do that. Okay, well, that demonstrates how we can take a graph and use projection lines and so forth, and common sense. And hopefully your background is such that you're able to understand what I just said. If not, we'll fix that. You're going to have to work a little harder. Well, as long as you got time, we're going to get you there. Okay, so we can interpret this graph. There's a lot more we can say about the graph, but that's enough for right now. Just give you the flavor. And we can do something similar here. Okay, this is 64,000, and this is time 60, and time might be in years. So we're looking at a 60-year period here. We can say that then at time just a little over 60 years, this is worth $64,000. Now, what was it worth here when the time was 0? Well, when the time is 0, well, we can subdivide. We can subdivide this, and we get 32. I'll use K for thousands because I don't have a lot of room to write. And I could subdivide this, and I get 16,000. And subdivide this, and I get 8,000. So here, I'm going to say that looks like about 5,000. Okay, so the value is 5,000 when the time is 0. And then the value is 64,000 when the time is, let's say, well, let's just see what some of these, okay. This would be 30. This would be 15. This would be 45. That's a 15-year span. That looks like about 2 years. So we could say the value is 64,000. Time is, I think I said 62. Okay, so we get that kind of information. Well, looking at illumination versus distance, we can say that the illumination is 800. That might be 800 lux. Okay, it's one measure of illumination. Might be 800 millijoules per square centimeter, if you know what that means, and there's no reason you should. Okay, so, but 800 something, 800 some unit, 800 of some unit. And here their distance might be in, maybe in feet. Okay, so that this point here would represent some number of illumination units at 16 feet. So this point would represent illumination 800, illumination at distance 16. What's illumination? Well, we're going to do a subdivision thing here. Okay, we're going to get 400 here, 200 here, 100 here. Excuse me, I get choked up when I'm talking about illumination. 100 here, and that's a little less than half of 100. So I'm going to say that's about 40. So I'm going to say illumination here is 40 when the distance is 16. Now I want to say, okay, here, the illumination is a little over 800. Let's see, 100 is this much. That leaks. I'm going to say that's illumination 830. You'd be welcome to make your own estimate. And I just realized I wrote too high up here, but this says Y equals illumination. Okay, illumination is 830. And at time is, distance is here. Well, if this is 16, then this is 8. And this would be about 4. we'll say illumination 830 at distance 3. Okay, well, those are 3 applications. Now, I'm going to relate these applications to 3 of the 5 most basic functions that we study in this course. Okay, now there are a few more basic functions, but there are 5 most basic functions, and there are 3 in particular that I want to focus on right now. So we'll talk about that in just a second, but I'm going to write some stuff on the board, and I'm going to pause the recording so you don't have to watch me do all the writing. Okay, I've sketched 3 graphs here with some dots on each graph. 6 dots here, 5 dots here for reasons you'll understand later, and 6 dots here. Okay, there's a very simple rule for constructing these graphs. I'm not going to tell you that rule right now, but that's probably the next thing I am going to tell you. Okay, each of these graphs represents a basic function. So we have a basic function here, a basic function here, a basic function here. If I look at the trend of these points go down and then back up. These points seem to follow a curve that goes like this. And these points seem to maybe follow a curve that goes up here and maybe does something, we don't know what, but then comes back down over here. Okay, so I'm going to just kind of follow the trend of these curves. Extending these points, extending the trend of these points to a nice smooth curve. So I'm going to extend down here and here, go through here, back up here, and up here. And that's a little lopsided. It's a little pattern this side than it is on this side. They didn't do a great job, but it's not too bad. Okay, should be identical. This side should be a reflection of this side. Symmetric. Okay, so I'm going to extend this function. Okay, it's simple enough. This is pretty easy to draw. Okay, there we have it. Now over here, for reasons that I'm not going to explain just yet, we're not going to connect this point to this point. You could think maybe because, well, we're not sure what's going to happen after you get here. Does it come up here and then just go straight across? Does it come up here and go up a little ways and turn around and come down? Well, actually, it doesn't do either of those things. But we'll leave that as a mystery for the moment. So what we get is, actually, it's going to be easier to draw from here. Okay, we get this, and we don't know what happens after we get here. There's some ambiguity, so we don't even draw it. Then we have this. Okay, so these 3 graphs. Now you can see immediately that this graph looks like part of this graph. Okay, maybe you have to stretch this graph out a little bit to get the same curvature, but we see that it has the same basic characteristic. This graph looks like it could be the left-hand side of this graph, but maybe not coming down and hitting the horizontal axis. It might be part of this graph. Okay, well, I'll tell you, you can probably guess which one it is, because I'm not trying to trick you or anything. The left-hand part of this graph is going to match this graph. Okay, so if I restrict this graph to here, just to this half, and then move this up here so that this low point is up a little bit off of the horizontal axis. It could be a model of this depth versus time. If I manipulate this graph just a little bit, kind of stretch it out a little bit this way, then it could mimic this graph. Now, we want the graph to start at a point that's only about maybe, what do we say, 564. From here to here, this is 13 times higher than this. So we want to take a section of this graph where the highest point is 13 times as high as the other. Well, we can do that. We can do that by just taking maybe this much of the graph from about here to here and using this as a model for this. Again, we might want to stretch out the x-axis a little bit, but we have a final value that's about 13 times as big as the initial value. Here, we can take just the right-hand side of this graph and model the illumination. Okay, so we take this, move it up here. We take this, move it up here, stretch it a little. Take this, move it up here. Alternatively, we can just take the scales of these graphs and label them on this graph. Now that, well, we'd have to change the positions of the x and y axes in a couple of cases. So for example, take this graph and put the y equals value axis here, and then the t equals time here. Label this point 62, so 62 goes about here, and 64,000 goes about here. And if this graph has exactly the right shape, it's going to work. We do similar thing over here. We don't really have to mess with the axes in this case. This y-axis will work just fine, and this x-axis will work just fine. So we could say, okay, now we're going to have y equals illumination, and x equals distance. And we could label points on the graph to be consistent with this one. Do the same thing here. We'd have to move the y-axis over to about here, so that the graph has the right position with the y-axis. We'd have to move the x-axis down a little bit lower because from this graph, this point is above the x-axis. But then we have a pretty good mimic of this graph. And we could label things. I'm not going to label anymore, but you get the general idea. Okay, well, the next thing I'm going to tell you is what the rules are for these graphs here. Okay, so pause the recording. I'll write a little bit, and then we'll talk about it. Okay, the rule for this graph is y equals x squared. The rule for this graph is y equals 2 raised to the power x. And the rule for this graph is y equals 1 over x squared. Those rules are simple enough. Let's see how we apply them to get the graphs. Okay, so the basic graphs we're going to use x values -2, -1, -1/2, 0, 1/2, 1, and 2. As long as we can calculate them, that is, as long as we calculate the y values exactly, without the use of the calculator. Okay, the first thing we do is make a table. Okay, now let's just look at the y = x² graph. That's the easiest one. If y = x², well, we can easily make a table. Okay, remember x is going to take these values as long as we can calculate these values exactly without using a calculator. And actually, I kind of misstated there. I wish I'd have stated that a little different. I'm going to say exactly as decimal numbers. Hopefully that's readable on your screen, but that's going to be part of our criterion. Okay, so we have -2, -1, -1/2, 0, 1/2, 1, and 2 are x values. What are our y values? Well, if x is -2, then y = x². So I'm going to write my y value here, but I'm going to do the calculation off to the right. So y = the square of -2, which means -2 multiplied by -2, which is 4. Now that should be obvious to you, but it isn't always obvious to people who've overused calculators, okay? So anyhow, we get 4. Okay, negative times a negative gives us a positive. 2 times 2 gives us 4. Okay, and then now I'm just putting 3 dots here because I don't want to take a lot of time out of your life to write something obvious. But when you write this out, as you will do on quizzes, tests, and so forth, you fill in here. I want to see the -1 times the -1, and that equals 1. And then I'll probably accept that. If I find there's a lot of uncertainty about how to do this arithmetic, and I see a lot of errors, then I'm probably going to want people to start writing, because a negative times a negative is a positive, and 2 times 2 is 4. Okay. But at least write the -1 times -1 here. -1/2. Okay. Now, how do you calculate that? Using the rule for fractions. When you multiply fractions, you multiply the numerators, you multiply the denominators, and you get the result. I also use the fact that a negative times a negative is positive, so I just wrote that out as positive number. Okay, well, here y equals zero squared, that's 0 times 0, that's 0. And then three dots means you fill it in. But clearly, I believe everybody will be able to fill these in. Okay, so there we have it. Now, the last step is you draw the graph. Okay, now I've used up a lot of space here, but I've got enough room up here to get a graph. We graph. Okay, so I'm going to put an x-axis here and y-axis here. And I'm going to put 2 here. And I'm going to put -2 here. I'm going to subdivide the interval from 0 to 2 in half. You get 1. And the interval from -2 to 0 to get -1. I'm going to put 4 up here. Now this distance is 4, so 4 ought to go right about here. And then I subdivide that to get 2, subdivide there to get 1, subdivide here, and I get 3. And I draw, well, I locate the points. Okay, I've got the points here. Just like I did before, I'm going to do the basic points using orange chalk. Okay, when x is -2, y is 4. So -2 is here, 4 is here, we got a point. -1, 1, well, okay, -1 here, 1 here, there's a point. -1/2, 1/4. Where's -1/2? Well, got to subdivide the interval from -1 to 0 in half, and I get -1/2. And I'm going to need 1/2, so I'm going to subdivide the interval from 0 to 1. And I'm going to need 1/4 for the y value. So I'm going to divide this interval. There's half. There's a 1/4. I'm not going to clutter up the graph by labeling those points, but I'm going to have a point here and a point here. And I'm going to draw those points pretty carefully because it impacts the shape of the graph. The location of these points is very important for the shape of the graph. Okay, and then my points 1, 1, and 2, 2. It's not 2, 2, it's 2, 4. You gotta holler at me when I do something ignorant like that, because I do it all the time. Be careful. Okay, so now I've got this, which of course is just like the graph I started with here. I can then draw my extended function. And I have my basic function in orange and my extended basic function in blue. For the basic functions, they start here and they end here. Okay, so we don't put arrows on these things, although it's fairly harmless to do so because we will do the complete basic function. But right now, we're going to confine the function to this interval from -2 to 2 and whatever y values occur. Okay, well, we did this for the y equals x squared graph. Now I'm going to go ahead and write out some stuff for the other two graphs, and then you get to see how that works. So we're going to pause the recording. Okay, I didn't write all that much, just y equals 2 to the x, y equals 1 over x squared. We want to talk a little bit about the arithmetic of evaluating these functions. Okay, so x equals 2, 2 to the x equals 2 squared, which is 4. Okay, that's easy enough. If x equals 1, 2 to the x equals 2 to the 1, which equals 2. If x equals 1/2, 2 to the x equals 2 to the 1/2, which is the square root of 2, which cannot be expressed exactly as a decimal. You might think it can because you can punch this into your calculator and you get 1.414 and then a bunch of other stuff. That's not exact because that number never ends. It's an irrational number. Now, so you don't include that in the domain of y equals 2 to the x. Because the definition was we use only the values of x that give us numbers that we can express exactly as decimals using standard arithmetic. Okay, well, same thing is going to occur for x equals -1/2. We also exclude x equals -1/2 for the same reason. Now, if x equals -1, y is going to be 2 to the x, which is 2 to the -1. And what does a negative exponent mean besides you got to put a minus in front of the number when you do the exponent, when you plug it into your calculator? Okay, people don't seem to understand this coming out of prerequisite courses. But 2 to the -1 means reciprocal, 1 over 2 to the 1. 2 to the 1, of course, is just 2, so this is 1/2. If x equals -2, y is 2 to the -2, which is 1 over 2 squared. And we're losing board here. Okay, we'll just prop this up a little bit. 1 over 2 squared, which is going to destroy my bucket. Hang on a minute. Okay, maybe I can get away with that. I got a big long streak there that. And that's 1 over 4. So you're going to have a homework problem that asks you to do the table and the graph for 2 to the x. You have to know how to do this arithmetic, and you don't just memorize it for this function. You learn the laws of exponents, the rules for exponents and fractions, so you can do this. Okay, and one of your first assignments from my open math is going to be just that. You're going to learn about exponents and fractions. Okay, now we got y equals 1 over x squared. Okay, we have to calculate that. A couple of examples, and I'm not going to go through the whole thing, but if x equals 2, well, 1 over x squared is 1 over 2 squared is 1/4. That's easy. If x equals 1, it's even easier. What if x equals 1/2? You get 1 over 1/4. Well, that's not yet a decimal number. That's a complex fraction. What do you do with a complex fraction? I would put money on it that the majority of people coming into pre-calculus courses can't tell me what that is, except maybe by guessing. Okay, and because fractions get left out of the curriculum, and it's a terrible omission. But fortunately, this is a 5th grade topic, and as adults, you can easily remaster it, and you need to do that. And of course, there's an assignment on that. Okay, so 1 divided by 1/4 is 1 times 4 over 1, which equals 4. And there are more details in the calculation of the fraction, but you have to be good at fractions, because for too long in the course, you're going to have to do fractions with algebraic symbols. Okay, you have to know the rules. Now, some of you do, and hopefully all of you do. I'd be very pleased if you do. My experience is that people simply don't. Okay, the majority simply don't. Some people know the rules very well. Okay, well, these are the rules that you need to apply to make the tables and construct these 2 graphs. Of course, you know what they're going to look like because I already showed you what they look like, but you need to construct the details, and you'll have an assignment due on the first weekend, a written assignment where you write all this out and submit it. Okay, so that's it for the introduction to these basic functions. I will mention that there are 2 other basic functions. You have y equals x cubed. And y equals 1 over x. And they're both very easy to do if you know how to do these 3. Okay. Oh yeah, one more thing about y equals 1 over x squared. If x equals 0, 1 over x squared is 1 over 0 squared, which is 1 over 0. Which is undefined. Because you can't get 1 out of zeros, not because of some rule that somebody gave you at some point that says you can't divide by 0. You can't divide by 0 because of what division means. What division means is, how many of these does it take to make this? Okay, how many zeros can you add up to get 1? Well, 0 plus 0 is 0, and add another 0, it's 0, add another 0, it's 0, you never get there. You can't get 1 out of zeros. So it's not possible to evaluate 1 over x when x equals 0. That's all there is to it. And that has implications for the graph, but we're not going to get into that now. I've already kind of alluded to it, but otherwise don't worry about it just yet. Now, everything that we've done so far is critical. It's the basis on which we develop the entire framework of the course. So you need to really understand this. So in addition to the MyOpen Math assignments for the first week, the 3 or 4, I guess there are 3 or 4 assignments due before the end of the week. There'll be another one due Sunday night. Actually, it'll be due Sunday night for the 7-week course for sure. I don't remember exactly how I set it up for the 14-week distance course, or the 14-week in class course, the 14-week synchronous course, okay. So I'm a little unsure of that, but again, this is the nucleus of the course. We take these ideas and we understand them very, very well, where we can make these graphs in our sleep. We can do estimates with the graphs, and we'll say more about estimates, and where we can interpret the graphs in terms of various things that are modeled by these graphs. And then, of course, we learn to do the algebra of the functions. And that's going to take us pretty much all semester. Well, then we combine functions and get polynomials, rational functions, exponential functions, logarithmic functions, and so forth. It all comes out of this, almost all of it, okay? So it's very important. This is what we need in order that when you get to the midterm or the final exam, the MyOpen Math is going to give you a lot of good information, but it's not going to pull things together for you. It's not going to give you the overall picture. You need the overall picture so that you understand what you're doing, so that you can interpret the problems, you can interpret the things that you're asked to do within a broader context, and you're going to have better success. That's all there is to it. You're going to understand how things fit together. This is the glue that fits everything together. Okay, well, looking forward to the course. Looking forward to working with everybody. Glad to have everybody here. Be prepared to work very hard, especially if you're in the 7-week course, which you remember is going to be twice as much work per day or per week as the 14-week course, because we're compressing all 14 weeks into 7. So be prepared for massive homework assignments. And if you're in the 7-week course and can't keep up, find that out during the first week or so you can switch into the 14-week asynchronous course or into the synchronous course if that fits your schedule. Okay, well, good luck. And you have your assignments in My Open Math. And I'll give you a written assignment on the things that we talked about here.